Okay, so let's look at another example, finding where it's increasing, decreasing, and constant. Here we're given f of x is actually a quotient, and we're given that the numerator is x plus 3 all over the denominator, which is x minus 4. So notice that this is undefined. When x is equal to 4. So there's a value which sets our denominator equal to 0, then it's undefined there. It's not in our domain. Recall values which set our denominator equal to 0, but not also our numerator. This is actually a vertical asymptote. Okay, so just kind of a reminder of what we've talked about in the past. But we want to find where this is increasing and decreasing. So we need to take the derivative of this and set it equal to 0 and find where it's undefined, where the derivative is undefined. So now when we take the derivative, we got to go back and look at our rules. So division, we had to look at the derivative, and I'm not going to take the derivative yet. I'm just going to put down the rules again. So it's the derivative of the numerator. So d dx of our numerator, x plus 3, all times our denominator, x minus 4, minus our numerator, x plus 3, times the derivative of our denominator, so d dx, and take the derivative of this x minus 4, all over the denominator squared. So x minus 4 quantity squared. So applying the quotient rule, the derivative of x plus 3, well, derivative of x is 1, derivative of a constant is 0, all times the denominator, x minus 4, minus, so our numerator, x plus 3, all times the derivative of our denominator. Well, derivative of x again is 1, derivative of a constant is 0, all over the denominator squared. So all over x minus 4 quantity squared. I'm wondering if my battery is going out on my pen. So order of operations, let's distribute in the numerator and combine like terms. Let's keep the denominator factored. So let's not expand that. So we have the derivative is equal to, well, 1 times x minus 4 is just x minus 4. We have this negative here, so we have to distribute the negative inside that parentheses. So we get negative x minus 3, all over x minus 4 quantity squared. So looking at this, x minus x is 0, negative 4 minus 3 is negative 7, all over x minus 4 quantity squared. So we want to find our critical numbers. So that is where it was set equal to 0. And where it's undefined. So notice that this is never equal to 0. If I set that equal to 0, 0 is equal to negative 7 all over x minus 4 quantity squared. We multiply both sides of our equation to clear the fraction by this x minus 4 quantity squared. So whatever I do to one side, I have to do the other. So this might be a good time to take a break so I can go find a battery. Hopefully I have a battery for this pen. Or I borrow my husband's. Yeah, it's dead. So we're going to find out when that's 0, where it's undefined, and we'll then put our values, critical numbers, on the number line and test it. But let's take a break. I'll come back and we'll pause the video. We're looking for our critical numbers. We're solving this equation. We're clearing our fraction, getting rid of the denominator here. So what we do to one side of the equation, we also have to do the other. So 0 times x minus 4 quantity squared is 0. This is equal to, well, this cancels. The whole point of that was to get rid of the fraction. So -7. Well, 0 is not equal to -7. This is a false statement. So there's no values of x would set this equal to 0. But if we look at this, the derivative is undefined at values which set our denominator equals 0. And so it's undefined when x is equal to -4. I'm sorry, when x minus 4 quantity squared is equal to 0. And this is when, well, if you take the square root of both sides, we get x minus 4 equals 0. Add 4 to both sides, x is equal to 4. Okay, so this is where f prime of x is undefined. We also talked about that being undefined for our original function and that was a vertical asymptote there. So we only have one critical number. Let's put that on the number line, x equals 4. And we want to test on the left and the right of that. So you can choose any number to the left of x equals -4. So if we chose, how about x equals 0? If 0 is in that interval, that's the fastest and easiest one to use. And so we're looking at this f prime of 0 is equal to plugging in here, we have -7 all over 0 minus 4 quantity squared. So again, really, we don't care what this number is. We just care, is it positive or negative? If our slope is positive, it's increasing, negative, it's decreasing. Well, if I square a negative in the denominator, that's positive, and my numerator is negative. So I have a negative number divided by a positive number, which is smaller than 0. So that tells me that the graph on the left-hand side of x equals 4, which was a vertical asymptote, is decreasing. It's going downwards, left to right. So now choose a value on the right of x equals 4. So any number to the left, the right of x equals 4. So how about 5? Plug it into the derivative to see if it's positive or negative. So we're looking at f prime of 5. Again, we're only worried, great, it's not working. If it's positive or negative. Well, if I plug that into my numerator, there's no x there, so this is -7 all over my denominator, 5 minus 4 quantity squared. So doing that, I have, this is equal to a negative in my numerator, all over 5 minus 4, that's 1 squared, which is 1. So this number is less than 0. And so again, that tells me that my function is decreasing on the right of x equals 4. So if I was to write this though, where it's decreasing, because it looks like it's decreasing everywhere, the only thing is it's not defined at x equals 4. So it's when you're writing out the solution, we have to exclude that number. So it's decreasing from -infinity till we get to 4. So parentheses, union, and then it's decreasing again 4 to infinity. So I can pretty much tell you exactly what that graph is going to look like just because I know that it's decreasing there. And we know that at x equals 4, I'm just going to do this really quick, and we'll talk about this more when we get into the 4th section of this chapter, where we'll be graphing these functions. But we knew we had a vertical asymptote at x equals 4. So I'm going to put that dotted line there. And we know it's decreasing everywhere. One other value that might help me, or a couple other values, is where is the x-intercept? X-intercept is when our function is equal to 0. Where's my function? Too far. So when is my original function, x plus 3 all over x minus 4, equal to 0? So if I multiply both sides by x minus 4 to clear my fraction, I'm looking at when is my numerator, x plus 3, equal to 0. So that's when x is -3. So at -3, I'm crossing this x-axis. I could figure out where my y-intercept is by looking at f of 0. So looking at f of 0, plug in 0 wherever you see an x here, we get this is 3 all over -4. So at -3/4. So let's say that this is -1. So right here. We know it's decreasing everywhere. And it has to hug this vertical asymptote. We also should know from what we were talking about before, this has a horizontal asymptote at x equals 1. Notice that the degree of the numerator and denominator are the same. And if we looked at the limit, we might as well just do this, as x is going to infinity, of this function, we get infinity over infinity. So if we multiplied everything through by 1 over x, a fancy 1 over x, then we're going to get the value. Let me just pause, and I'm going to grab my husband's pen and see if that works better. Okay, so doing that, we got 1. We get that this is going to 1. We have a horizontal asymptote at 1. Again, we know it's decreasing everywhere. We know that we have an asymptote at x equals 4. So I know that that's going to be decreasing everywhere. And it's going to be hugging this horizontal asymptote at 1. So from there, we got a graph of what it looks like. Okay, so now you're looking at an example where you're finding where it's increasing and decreasing of y equals the square root of x squared plus 1. So again, we need to find the derivative of this. Before we find the derivative, this is a case where we would want to rewrite this using x squared plus 1 all raised to the 1/2 power. So we're going to take the derivative of both sides. So derivative of y, another way to write that is y prime is equal to, we're going to need to use our chain rule here. So bring our power down front, the derivative of the outer. So 1/2 of the inner, x squared plus 1, subtract 1 from the outer, times the derivative of the inner. So I'm going to just write that d dx of the inner, which is x squared plus 1. So maybe it's not the pen at all. So let's do that. We have 1/2 x squared plus 1 to the negative 1/2 power times the derivative of x squared plus 1, which is 2x. So let's clean this up before we set it equal to 0 and find where it's undefined. Notice that we have a 2, because think of this as 2x over 1 in the numerator and denominator. We can cancel because this is strictly multiplication right here. And then we are going to rewrite this so that our exponent is positive by bringing it down to the denominator. So, and in the negative 1/2, that becomes positive 1/2 in the denominator. And we can rewrite that as a square root. And we're left with this x in the numerator. So x divided by the square root of x squared plus 1. So we want to find where is this equal to 0? And where is y prime undefined? So when you have a quotient, basically all you're looking at is when is that numerator equal to 0? Because we would clear the denominator by multiplying both sides by whatever was our least common denominator of the fraction. In this case would be square root of x plus 1. So this is when x is 0. And when is this undefined? Well, our functions are undefined where we have 0 values that give us 0 in the denominator, values which gave us a negative number underneath the radical. And so we need to look at when is this denominator equal to 0? So solving a square root equation, we can clear the square root by squaring both sides. Recall when you're solving rational functions and you raise both sides of your equation by an even power, that's telling you that you might get extraneous solutions, that you might have to check this at the end. So if I square both sides, the square root, those cancel the radical, I'm just left with x squared plus 1. This is equal to 0 squared, which is 0. I can try factoring x squared plus 1, or another way to do this is I can isolate my square and take the square root of both sides. I notice this is not factorable. I also notice I'm going to get an imaginary number. If I subtract 1, x squared equals negative 1. I can take the square root of both sides, put plus or minus in front of one of the radicals. And so we get the square root of x squared is x is equal to plus or minus the square root of negative 1, which is I. So this is not a real number. There's no value which sets my denominator equal to 0. Now we have to worry about where is this undefined, where is the value less than 0. We can't take a square root of a negative number. We don't have to worry about it here. Technically, we would look at when is x squared plus 1 less than 0. In this case, there's no value which is ever going to give us anything less than 0. And again, we could solve for x like this was an equal sign, and we could see that there was no value which would make this less than 0. It makes sense because if you square any number, it's positive. Plus 1 is always a positive number. Okay, so this is defined everywhere. We don't have any values, critical numbers. Oops, we do have one, x equals 0. So now we need to test on each side of that. So choose a number to the left of x equals 0. So any number to the left of this. So how about x equals -1? And we're plugging it back into the derivative to see if it's positive or negative. So our derivative was this. So if I plug a -1 into the numerator, I get a negative, all divided by, well, we saw that the denominator was always going to be a positive number. So negative over a positive. That's a negative number. And so I know then it's decreasing from negative infinity right now to 0. Union. So trying on the right, anything positive. So how about 1? So at x equals 1, well, we get 1 over. So that's a positive over a positive, and that's greater than 0. So it's increasing here. So if we graph this function, this is defined at x equals 0 for our original function. This is decreasing and then increasing. And so we talked about if we have something that decreases, it's defined at that critical number, and then it increases. I can see that at this x equals 0, there is a minimum value. And so increasing, because I wanted us to find where it was increasing also, we can write that out. From 0 to infinity. So again, we could start putting this together to graph this function and get a general idea of what it looks like.